The Invisible Arteries, Japan's Revolution. Beneath the waves, to truly appreciate the engineering prowess of Japan, one must look beyond the skyline. While the towering sea walls protecting the Tohoku coast stand as visible monuments to resilience, a quieter, more invisible battle is being fought beneath the surface of the ocean. Japan is an archipelago, a nation fragmented by water, where the sea has historically been both a lifeline and a barrier. For centuries, the only way to cross these straits was by boat, subject to the whims of the weather. In the modern era, massive bridges were constructed to span the bays, but bridges have inherent vulnerabilities. They are exposed to typhoons. Their pillars must withstand the violent shaking of earthquakes, and they can obstruct the passage of the massive cargo ships that power the nation's economy. To maintain a steady flow of goods and people, regardless of the storms raging above, Japanese engineers realized that the ultimate solution was not to go over the sea, but to go through it. This realization birthed the era of the underwater tunnel, a category of infrastructure that serves as a crucial economic artery for the country's busy port cities. These are not merely holes dug through the earth. They are high-tech, pressurized vessels designed to exist in an environment that is fundamentally hostile to human life. Japan has become a global leader in this field, mastering the complex immersed tube method, a technique that defies intuition by building the tunnel on dry land before sinking it into the ocean depths. The journey of constructing these subsea highways begins with a phase of meticulous preparation that rivals a space launch. Before a single cubic meter of concrete is poured, engineers must map the invisible world of the seabed. Comprehensive seabed surveys are conducted to study the subsea topography, while drilling teams collect soil samples to analyze the rock strata. This geological detective work is critical to determine the bearing stability of the ocean floor. If the seabed is too soft or uneven, the tunnel could settle and crack under its own weight. Engineers must identify any latent hazards that could jeopardize the structure decades down the line. Parallel to the geological challenges are the ecological ones. In Japan, modern engineering must coexist with nature. The project teams prioritize environmental considerations, assessing the tunnel's potential impact on marine ecosystems to ensuring that natural habitats are disturbed as little as possible. To achieve this, they implement strict noise mitigation measures during the dredging phase and, in some innovative projects, install artificial reef structures along the tunnel route to create new homes for marine life, effectively turning the infrastructure footprint into a biological asset. Once the path is cleared, the construction moves to a massive dry dock, often miles away from the tunnel site. This is where the immersed tube method distinguishes itself. Instead of boring through the earth like a worm, workers prefabricate the tunnel in segments. These are not small blocks. They are colossal reinforced concrete elements, often weighing tens of thousands of tons and stretching over 100 meters in length, depending on the specific project requirements. Manufacturing these segments on land allows for a level of quality control that would be impossible underwater. They are built with extreme precision to ensure perfect alignment and watertight sealing. Inside these massive concrete boxes, the anatomy of the tunnel is already visible. The interior is divided into several compartments designed for specific functions. Typically, 2 main chambers for highway lanes, a separate section for a railway line, and a dedicated service corridor for future maintenance and emergency inspections. Once the concrete has cured and the internal systems are roughed in, the ends of each segment are sealed with temporary bulkheads. Then, the dry dock is flooded. In a triumph of physics, the massive concrete structures, heavy enough to crush a building, lift off the ground and float. The transportation phase that follows is a delicate ballet of heavy industry. Using floating pontoons and specialized cranes, the segments are towed out to sea. This is a moment of high tension. The segments are vulnerable to wind and currents as they are moved to the pre-dredged positions on the seabed. The sinking process requires surgical precision. Engineers must lower these behemoths into the black water, guiding them into a trench that has been carved out of the ocean floor. A deviation of just a few centimeters can result in a failure to connect, jeopardizing the entire project. The connection of these segments is where the true genius of the method lies. It relies on the immense power of the ocean itself. Each segment is fitted with a specialized rubber gasket on its face. As the new segment is lowered and aligned with the one already on the seabed, the water between their bulkheads is pumped out. This creates a vacuum, and the crushing hydrostatic pressure of the deep ocean pushes the two segments together with incredible force. The ocean acts as a giant clamp, compressing the rubber gasket to ensure absolute water tightness. Once the segments are securely locked and stabilized, the tunnel is buried. Layers of sand and gravel are placed above and around the structure. This backfill serves a dual purpose. It protects the tunnel from falling anchors or dragging fishing nets, and it provides the necessary weight to counteract buoyancy. Without this weight, the air-filled tunnel would try to float back to the surface like a cork. Only when the structure is buried are the temporary end bulkheads removed, transforming the individual tubes into a seamless, watertight tunnel stretching across the bay. However, this technique is not a universal solution. It is suitable primarily for areas with a stable seabed and gentle water currents. In environments with strong turbulence or complex underwater terrain, the immersed tube method becomes impractical due to the difficulties in anchoring and maintaining waterproof integrity, forcing engineers to look for alternative, often more expensive solutions. Upon completion, the tunnel transforms from a construction site into a living machine. In many modern Japanese projects, these tunnels are designed with 2 levels, effectively doubling the traffic capacity without expanding the structural footprint. Drivers can maintain a stable speed of about 60 kilometers per hour, protected by a suite of safety systems. Emergency exits are positioned every 200 meters, ensuring that in the event of a fire or accident, escape is never far away. Before opening to the public, the structure undergoes a series of rigorous tests, including checks on waterproofing integrity, pressure resistance, fire safety, and ventilation performance. Yet, the completion of construction is merely the beginning of the tunnel's fight for survival. The real enemy of an underwater tunnel is not the water itself, but the salt and the passage of time. Salt water is a relentless corrosive agent that seeks to destroy steel and crumble concrete. To ensure the tunnel endures, maintenance determines its longevity. Dedicated technical teams conduct regular inspections of the concrete lining and waterproof membranes to ensure no deformation or cracking occurs. This human effort is augmented by a digital nervous system. Hundreds of sensors installed along the tunnel walls continuously monitor pressure, temperature, humidity, and vibration. These sensors transmit real-time data to a central control room, allowing engineers to detect even the earliest signs of structural fatigue. In parallel, specialized vehicles equipped with high-pressure water jets and suction systems patrol the tunnel, cleaning the floors to prevent blockages and sediment buildup. Through this combination of advanced sensor technology, precise manual maintenance, and audacious construction methods, Japan's underwater tunnels operate safely and efficiently for decades. They endure the harsh environment of the ocean depths, serving as invisible arteries that keep nations' blood flowing. From the massive tsunami walls that shield the land to the deep undersea tunnels that connect it, these projects showcase not only Japan's advanced engineering, but also the unwavering determination of a nation to thrive in one of the most geologically challenging regions on Earth.